Let's find the integer square root of a number, say 40. That means the largest whole number whose square does not go past 40. 6 times 6 is 36, which fits. 7 times 7 is 49, which is too big. So the answer is 6. Instead of trying every number from 1 upward, we can binary search on the answer itself. Here's the neat part. We are not searching inside an array. We are searching over the possible answers. The square root is somewhere between 0 and n. We guess the middle. If the middle squared is at most n, then the middle is a valid answer, so we remember it and try for something bigger on the right. If the middle squared overshoots n, we must go smaller on the left. Each guess halves the range, so we zero in on the largest value that still fits. Our answer lives between 0 and n, so those are our low and high. We keep the best answer so far in ands. We guess the middle. If the middle squared is at most n, the middle fits, so we save it and push low higher to try for a larger root. If the middle squared is too big, we pull high down. When the range closes, ands holds the integer square root. Let's build the integer square root live, searching on the answer. The answer sits between 0 and n, and we remember the best fit so far in ands. While the range is open, we guess the middle value. If the middle squared still fits within n, it is a candidate, so save it and try for something larger. Otherwise, the guess overshot, so pull high down, and at the end, return the best answer. Now, let's test it and hit run. There we go. The integer square root of 36 is exactly 6. For 40, it is still 6 because 7 squared would overshoot, and the square root of 1 is 1. The whole shape. Low is 0, high is n, and ands is 0. While the range is open, take the middle. If the middle squared is at most n, save it and move low up. Otherwise, move high down. When the range closes, return the saved answer. Each guess halves the range of possible answers, so we finish in a number of steps that grows like the logarithm of n. That is order log n time, far faster than trying every value. We keep only a few variables, so the space is order 1. 3 things to remember. First, compare the middle times itself against n using whole numbers, so you avoid the rounding errors of a floating point square root. Second, in some languages, the middle times itself can overflow for very large inputs, though Python handles big integers for us. And third, always return the last value that actually fit, which we saved in ands, not wherever the loop happened to stop.